Welcome to Spirit of Math. In this video we will tackle a very challenging integral, namely this integral is the integral between 0 and 1 over square 2 of this rational fraction. This integral is very challenging since to compute it we need to review many techniques of integration. Namely, we will see how to factor a polynomial function, how to use partial fraction decomposition of a rational function, the theorem of change of variable in an integral, and as a bonus we will need this beautiful formula and we will show it also. So let's start. So we want to compute the integral of this quantity. So first we will split it in two parts by using this remark. That's we factor here, and we get this. Of course, we use the algebraic identity 1 minus t power 8 equal 1 minus t power 4, 1 plus t power 4. So now, to compute the integral of this quantity, we need to compute the integral of this fraction, of this rational fraction, and the integral of this rational fraction. First, let's start by factoring this polynomial. To dessous, we remark that t power 4 plus 1 is equal t power 4 minus I power 2, and we use the algebraic identity. Now we will find a square root of I, namely this a equal 1 over square 2 1 plus I. If you compute a square, we get I, and minus I is the conjugate of a square. Now we have t power 2 minus a square, and we use the algebraic factorization, and we get this expression. Now we compute this one, and we get this decomposition. Here we have a plus conjugate a, which is a real number, and here we get the modulo of a square. Now if you compute a plus a conjugate, you will get a root of square of 2, and the modulo of a is equal to 1. And now we have shown that t power 4 plus 1 is equal to the product of these two polynomials. So now we have done with this quantity. So our integral split into two integrals, e1, a2, and we will compute these two integrals. This one can be done by using a change of variable. If you take u equal t power 2, we get that I2 is equal to this integral. Now it's the integral of a rational fraction. We need to partial fraction this quantity. So we can write that this fraction equal a over 1 minus u plus bu plus c over 1 plus u square. And we will look for a, b, and c. The technique here is, first we multiply the both sides but 1 minus u here, so we get 1 minus u simplify and we get a, and we take u equal to 1. If we take u equal to 1, here we get 0, and here we get 4 over 2. So we get that a is equal to 2. Now let's compute b and c. So what we will do here, we will multiply here by 1 plus u square. So we get here this equality, and we take u equal to I. If we take u equal to I, here we get 0, and we will get 4I over 1 minus I equal bi plus c. And we identify the real part and the imaginary part, and we get that b is equal to and c equal minus 2. So here we have seen how to do the partial fraction of a rational function. Now we have that I2 is equal the sum of these three integrals, and here we have the antiderivative. Here it's easy to compute. The antiderivative of this function is easy to compute, and also the antiderivative of this function is the arc tangent. So we get that I2 is equal to minus 2, the logarithm of the absolute value of u minus 1. Here we get the logarithm of u square plus 1, and here we get the arc tangent. And if we replace, we get this quantity which we can simplify and get. Here we have the logarithm of 5 over 4 is the logarithm of 5 minus the logarithm of 4, and the logarithm of 4 is 2 logarithm 2, and this cancel with this quantity, and we will get that E2 is equal the logarithm of 5 minus the arctangent of 1 over 2. So we have now computed the I2. Let's tackle now I1. I1 is also the integral of a rational fraction, so we need to do the partial fraction of this fraction, and we can write this as at plus b. And here, since if we replace t by minus t, we get that a equal we get minus a here and b here. So here we use the fact that this function is even. And now let's compute a and b. For a, we take t equal to 0. So if we take t equal to 0, we get here 2b, and here we get 4 square 2, and we get b equal to square square 2. For the computation of E, we will take t equal square 2. And if you replace, we get this equality, and which simplify to get that here we simplify by square 2, and we multiply by 5, and we get 4a plus 12, and e equal minus 2. So now we have shown that E1 is the sum of two integrals. We call them G1, G2. And we will compute now G1 and G2. For G1, we will first compute the antiderivative of this function, and we use here that 2 square 2 is equal square 2 plus square 2. Now the antiderivative of this quantity is the logarithm of t is square plus square t plus 1, and we will compute this one. This one can be done by some trick. So here we have this one. For the second one, we write this quantity as that. If you compute this quantity, you get square 2t square equal to 2t plus 1 plus 2 square 2, and we get the same. And here we use that the antiderivative of this function is 2 arctangent square 2t plus 1. And now we have antiderivative of this function. The antiderivative of this one can be done by using a change of variable u equal minus t. And now we get that G1 by using a change of variable t equal minus u, we get this inequality, and we use the antiderivative of this function, and we can compute G1. We will see that is equal the logarithm of 2 plus p over 2. And we do the same for G2, and we get this quantity. And now E1 will be equal the logarithm of 5, because we have this the logarithm of 2 will cancel here, and pi over 2 will cancel 2, and we get this quantity. And now we have computed I2, and our integral is I1 minus I2, and we get this beautiful formula for I. Now we need to show that this quantity is equal to pi over 2. We will show that this function is equal to pi over 2 for x different from 0. To do so, we have that f of 1 is equal pi over 2, and we will show that the derivative of this function is equal to 0, so this function will be constant equal to f1, and we have done. Let's compute the derivative. The derivative is easy to compute, and we get equal to 0, and we have done. So we have computed our integral. Okay, so now to support the channel, please like, subscribe and share. And thank you.